motor design calculator, and I'm going to go through the steps of using it in just a minute. The thing is, though, I'm going to get to, at some point, this term boing, and I'm going to feel compelled to explain it. So I'm just going to explain it now, because if I screw it up, then I don't have to redo the whole video. I just have to redo the first part. So skip to the spreadsheet part if that's what you're really interested in. Okay, so here's a spring, and let's just say the length of this spring, I'm going to call it L, is 2 meters. And then suppose we stretch the spring. We stretch it another 1 meter. 1 meter equals X. I'm using X because that's what's used with the spring constant usually. And when we first start stretching it right here, the force is 0 newtons because we haven't really started stretching. But by the time we get to stretching it here, let's say we get to 10 newtons. So if you know about spring constants, it's force per distance stretched, and 10 newtons, we're stretching 1 meter. That's 10 newtons per meter. So for every meter that you stretch this thing, you've got to exert 10 more newtons. The rubber bands, however, we can cut to different lengths, and we can hook rubber bands together like this and this and this, or we can have multiple, we can cut these apart and we can make multiple individual strands and do weird kinds of stuff. So that's going to have an effect on the spring constant. So imagine now that I cut this thing in half, and think about these two little pieces of this thing and what their spring constant would be. Would it be the same thing? And the answer is no. Because when I take the full thing, which is 2 meters long, and I stretch it this much, which is like 3 whole meters for the entire spring, those little segments, they just get stretched from, this would have been 1 meter long, and this one was from here to here is 1 meter long. And then when I stretch the whole thing to 3, this one is going to go to 1.5 meters, and this is going to go to 1.5 meters. And the tension in these two individual parts is going to be the same as the tension in the whole thing. So when I stretch this one, a distance of 1 to 1.5, which means X is 0.5, I now have gone from 0 newtons to 10 newtons. So this would have a K of 10 newtons per 0.5 meters, which would be 20 newtons per meter. And every time I keep cutting it, or maybe making if I hook 2 springs together, that kind of thing's going to happen. K is going to go up or down. And I want some way to describe this that is going to just work. It's going to be the same. It's not going to change. So that's where boing comes in. And boing, I'm using this term. It's kind of like Young's modulus, but a little bit simpler. Boing is force divided by strain. And in Young's modulus, they use this symbol for strain. And epsilon is basically the distance stretched over the length of the spring. So if we look at this example here, the distance stretched, I'm going to calculate boing for what I've got right here. Boing is 10 newtons. That's the force. And then the distance stretched right here was 1 meter. Got to get my order of operations right. And the length of the spring was 2 meters. So 1 divided by 2 is 1/2. 10 divided by 1/2 is 20 newtons. And notice that these cancel out. So it's just 20 newtons. But it's understood that 20 newtons is force per strain. Force per, I think of strain as the fractional increase. So if you look again at this, if we're stretching 1 meter and the whole thing was 2 to begin with, that's an increase of 50%, or this fractional increase down here is 1/2. So if I use the example I did before, where I take this and I break it into these little segments right here, and I imagine this segment, I stretch it from 1 meter to 1.5 meters like I was talking about. So in this case, buoying is 10 newtons, so I'm applying 10 newtons to the whole spring, and to this little half that I'm focusing on here, it's got 10 newtons of tension in it, because every part of a string or a spring or a chain or whatever has the same tension when you stretch it. And that needs to be divided by this strain, and this strain, its X is 1/2 meter, and the original length is 1 meter, so 1/2 divided by 1 is just 1/2, and buoying is still 20 newtons. So this is kind of a fundamental property of this particular spring material. So I can take, this original 2 meter long spring that I talked about, and I could chop it up into a little tiny pieces, little segments that are this long, or I could hook several of them together and make them 50 meters long. And no matter what, let me write buoying again. If let's say buoying is 20 newtons, and if I set up 20 newtons equal to force over 2. So this means if I have some spring and I stretch at a distance x, if this is x, and this would have to be 1/2 x. If I stretch it twice its original length, then I have a strain of 2, and the force has got to be 40 newtons. So anytime you double the length of this of this spring, it's 40 newtons. If you would quadruple the length of it, it would be 60 newtons. If you would add on half, stretch it half its length, then that would take 10 newtons. And it doesn't matter if you're talking about stretching a little piece to twice its length or a really big piece to twice its length, it would still be the same force. All right, so that's what buoying is all about. Now I'm going to jump to the spreadsheet and explain how to do this. So first, unstretched length of one full rubber band flattened into 2 parallel strands. What I'm talking about there is take a rubber band like this and flatten it out so it's like that, and then measure this length. And I did this earlier, and this length was about, I'm rounding now, 0.1 meters. It was really 0.101. So, but I'm just going to put, let me put 0.101 is that length. So I'll enter that. And this was after I'd messed with the rubber band for a while. I'd stretched it a bunch, so when the rubber band was right out of the bag, it wasn't actually that long. You could choose to get fresh ones, or you could pre-stretch them. Maximum comfortable stretch distance. So the next thing I did was I stretched this rubber band as far as I felt like it should go. So I stretched, and I stopped before I thought it was foolhardy to continue. And that distance right there, which I'm going to call X, that was 0.45 meters. So that goes here. And as soon as I do that, you'll see max comfortable strain pops up. So if you decided that's a good amount of strain to put on your rubber band, when you're consulting this table down here, look at the strains. Don't pick some that are way higher than that, because again, you've already made the decision that that's a stupid thing to do. You can use strains that are less than that, but you probably won't get as much energy out of this whole thing. Then I've got stretch force to stretch one full rubber band to the maximum comfortable stretch. I used a force sensor when I did this, And I figured out that to stretch it this far, I had to apply a tension of 16.2 newtons. So that number goes right here. And immediately the 16.2 gets divided by 2 to 8.1 so that we can get the stretch force of a single strand, because you might want to cut your rubber band and just use a single strand. There are reasons to do that and reasons not to do it. So I've got strain and then I've got buoying. So buoying is 1.818 newtons. So what that means is if you take any piece of rubber band, no matter how long, and you double the length of it, you stretch it its full original unstretched length, then you have to exert 1.818 newtons. If you stretch it to 3 times its original length, meaning the stretch distance is twice the original length, then you have to exert twice this, so 3.636 maybe, something like that. And did I do that right? Yeah. And if you just stretch it 50% extra, then you have to exert 50% of this force. So this represents the fractional increase in length, or the, yeah. All right, now the car. So first thing is maximum possible motor force without exceeding drive wheel friction. You should do some tests on your car. Here's your car. I don't know which are the drive wheels, but let's just assume that they're bigger and your car looks kind of like this. Let me pick a different color. And somewhere up here on the front of your car, you've got a little hook. And you stretch a rubber band or some rubber bands right here, and then you have a string that goes to the drive axle. And you apply tension to this string, and you wind it around like this until this part of your rubber band has stretched all the way over to here. So when you're all done and you let go, the wheels are going to go like this, they're going to push off, and right here you're going to use friction to push the road back, and that road is going to push your car forward with friction. If you wind this thing up too much, then that force is too much and your car is not going to work. So you need to experiment. You need to figure out exactly what the maximum tension can be. So let's say you found that, and let's just say that's 40 newtons. I'm going to put that into the spreadsheet. We know your car can handle 40 newtons and no more. So it behooves you to use as much force as you possibly can and get as much energy as you possibly can, but no more. No more force. And then total available motor span. So a little bit about work and energy. Energy is comparable to work, and work is force times distance. And when you stretch these bands, you're applying a force, and the distance over which you do that work is important. Bigger force, bigger distance, it's going to give you more work, more energy. The number that we need for this is the distance from here, wherever you're going to hook your rubber band on, all the way to the drive axle. That's the total span that you have to work with. And let's just say that span equals, I don't know, 53 centimeters. So 0.53 meters. All right, everything populates down here. So I've got to, let me read this. Yellow, enter your own data. I just entered all these data. You could use my data here. These apply to the rubber bands that I have in class, but only if you've stretched them a lot first and they've kind of turned pallid. They're not as dark as they are to begin with. They sort of fade. Also, there's a note saying this model assumes that the band force starts at 0 and the motor is stretched until the bands reach the drive axle. That's probably the best way to do it. And don't start with a lot of tension in your string, unless you want to make sure that the band pops out and your car keeps going, but there's really no reason to have it do that, except it looks cool. Another note, look for strains within the comfortable range. So all of these, here are the strains. The comfortable range is, remember, less than, maybe I should make that the same color as that other stuff. Is that the right color? Yeah. So 4.45, 22 is too much strain. 11 is too much strain. Getting right around here, this is pretty good. So row 18 is kind of a nice place to be. And then there's another note. It's easiest when L, here's L, is close to the unstretched spring length, and C3 is right here. So the unstretched rubber bands are just naturally about 0.101 meters long. So if this L for our band configuration is about the same, so about like this or this, these in here, that's pretty good. That's convenient because we can just use whole rubber bands. And it's also good when we have whole numbers over here, because this one means you would have to cut your rubber band and just use a single strand, which can be a little hard to hook up to a string. It's doable. So the 1 and the 3 and the 5, those are more trouble. This 2 bands represents 1 rubber band. 4 is 1 full rubber band. 4 is 2 full rubber bands. 6 is 3 full rubber bands. So it looks like for this car, 4.4 is a reasonable amount of strain, but if I go across, that's 5 bands. So we've got 3 choices. We could go with, 6 strands, which would be a motor that would look like this. A rubber band, and another rubber band, and another rubber band. So 3 times 2 equals 6 strands. And then you hook your string to that. So that's what this one would look like. So that would be easy, and it would be within the strain. It would be less strain. The work to stretch the bands is 8.33 joules. So that's the input energy, how much energy we'll be putting into the car. Above that, 8.6 joules, that's better, but the problem is, and the strain is okay, the problem is we've got 5 bands, so you'd probably want to just cut up some pieces, and then tie them together with fishing line right here. Tie them together, so that it's, they'd actually look like 1 wad, like this, with a knot here and a knot here. And you can do that. The nice thing about this is then you can adjust the length to exactly what you want it to be. And then if you wanted to push the strain to up to 5.5, you're stretching these farther than you kind of felt was a good idea. You could just use 4 individual strands, which means you could use 2 whole bands, and you'd get even more energy in your car, but who knows? The bands might break if you do that. A little bit about what's going on here. This length plus this x equals this distance. So what? Oh, no, sorry. This distance. This is the span. So I've done some algebra, and I've decided that I want to basically use all this available space right here with my motor. I want it to stretch as far as possible so I can do the most possible work. So the band over here plus the string here adds up to that 53 centimeters. So on the spreadsheet, you'll always see this plus this equals that. And as you move down here, you can see that the bands get longer and the stretch distance gets shorter. And the energy goes down as well. Another thing you can look at over here, this is Boeing. So Boeing is kind of fun. A low Boeing is actually kind of good. But there's a balance. So if you have a really low Boeing, what that means is you can have a very short band and you can stretch it to many times its length, like 20. This thing is stretched. The stretch distance is 22 times as long as the band itself. So you get a whole lot of stretch. So your work distance is greater. And the Boeing doesn't have to be really big because Boeing is the amount of force per strain. So bigger the strain, the lower the Boeing can be. As the strain goes down, the Boeing has to go up. And once you get down here, things like 10 strands, that'd be 5 rubber bands all together. The length of that to make that work would need to be 16 centimeters long. So that'd be a really bad idea. I mean, you get less energy. It's not a trivial amount of energy, but it would be a silly thing to do. So 0.16, you'd have to do something like, oops, sorry. You have 1, 2, 3, 4, 5, and then you cut 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 little strips so that you can make your length from there to there. And really what you would want to do is you'd just want to cut 10 strips. I don't know if I've done 10. Tie it off here, tie it off there. That's what this one would look like. Make sure that between your tied off parts, you've got 16 centimeters. But again, it only stretches 36 centimeters, whereas these other ones stretch a lot more and have more energy. So the best bet here is to look at your strain, look at strains that are close to that, go over, find band lengths that are about the same as they ordinarily are, and then look over here and look for colored ones. So, you might try 4, which is 2 whole bands. You get more energy if you can survive it.